Okay, so hello and welcome back. So basically now that we understand how to deal with basically two transistors, now we can basically talk about, for example, three transistors, which is essentially the same thing, but a little bit different. And then I'll draw a circuit over here, and in case you haven't watched the previous videos, I'll tell you briefly about the situation. But if the explanation is not enough, then you can basically watch the previous videos in order to get more familiarity with the nature of these problems. So essentially what we have here is a what we have here is essentially a circuit that basically has a switch over here, and this switch basically this part of this, and you can imagine that this is a switch, and you have a resistor over here, and this goes to the positive rate, right? Now this part of this terminal of the switch goes into a resistor, and then it goes into the negative rate. So this is V of S positive, and this is V of S negative. And you can call this, for example, R1, and you can call this, for example, R2, and then this goes to the base of a transistor, an NPN transistor. The emitter of the transistor goes to the ground, the collector goes through a resistor, and then goes to the positive rate. Now, the voltage that we have over here, we take this voltage and give it to the base of another similar, basically, well, not similar, but NPN transistor. Again, the emitter goes to ground, and then the collector goes through a resistor to the positive rate. Again, the voltage from here, we take it and give it to the base of a transistor, and the emitter again goes to the ground, the collector goes through this resistor to the positive rate. And that's basically what this circuit does. And I can call this, for example, R of 3, R of 4, and R of 5, for example. And essentially you can think of this circuit as, basically this circuit works in the following way. So if I call this position A and position B of the switch, when the switch is in position A, what happens is that basically the base of this transistor becomes positive through this resistor, and so the transistor is turned on. Of course, what happens actually depends on the values of the resistors that you choose, and you want to choose the value of these resistors. Your goal here is to choose the value of the resistors in such a way that when the base of the transistor is tied to the positive rate through this resistor R1, that the resistor gets saturated or is turned on. So there is current from the positive rate to the emitter to the ground, and as a result, then this transistor over here, since this transistor is turned on, there is no voltage here, right? The voltage over here is very close to 0. Which means that this transistor is turned off. And we can call this, for example, Q1 for the sake of simplicity, Q2, and Q3, right? So since this transistor is turned on, this is turned off. Since this is turned off, then basically, so then essentially you have since this is turned off, then basically you have no collector current in this transistor, meaning that this would act as a open mechanical switch. The collector emitter junction of this transistor would act as a open mechanical switch, almost infinite resistance. And what that means is that the current V of S, basically we have it up here, so it would go through this resistor R4 and to the base of this transistor. And since now this transistor, the base is positive, so then you would have collector current, the transistor is turned on or saturated, and that means that Q3 is essentially turned on, right? And that's your goal, basically, when you want to design this circuit in such a way that when this switch is set to position A, that for example Q3 is turned on, and when you set it to position B, then Q3 would be on, and then this would be off, basically, right? And the way that it's off is that basically when you set this switch to B, then this transistor is turned off, this transistor is turned on, and so this transistor would be turned off, right? So that's basically how the circuit works. Now, of course, the fact that for example each and any of these transistors is turned on or off depends on the resistors that you choose here. Meaning that, of course, for example, R1 has to be chosen in such a way that there is enough base current for this Q1, so that there is enough collector current for Q1, so that the transistor gets saturated. And the same goes for the other two transistors as well. So now what we want to do is that we want to choose the values of R1, R2, R3, and R4 and R5 in such a way that essentially this thing happens. And of course you might say that, or you might think that this doesn't make any sense really, that you just put a bunch of transistors together. This one is turned off, this one is turned on. The circuit doesn't do anything. But this kind of basically exercise does basically two things for you. One, it tells you how to design circuits. Second, it teaches you how to do calculations related to transistors and how to use the Ohm's law in different situations, how to analyze circuits, and that sort of thing. Basically, it's basically well designed, basically. But I mean, almost in all cases, when you're learning these things, you have to start with the types of circuits that essentially do nothing, meaning that usually for example, when you're learning DC circuits, you usually have a power supply, and the power supply goes to a resistor and then back to the ground, meaning that this circuit essentially does nothing, just consuming power, really. But well, that's the way it is, and that's how you can learn basically electronics. So now let's see how we can basically find the values of these resistors, so that this situation basically occurs here. Okay, so now, as we explained before, in this type of circuit, you have to start from the right hand side and work your way through to the left hand side, because otherwise, if you start from here, and meaning that if you go in this direction, starting with R1, R2, R3, and R4 and R5, in this direction, you will have basically, you will come across some equations, and in these equations you will have two unknowns, and and as a result you'll not be able to solve the problem. So you have to basically move in this direction, and the reason is that basically the value that you have, essentially R5, has been given as 10 ohm. The value of this resistor we already have, but these resistors we don't have them. You have to calculate them. So you have to start with what you have. And beta 3 is equal to 20. Beta 3 is equal to 20. Beta 2 is equal to 50. And beta 1 is equal to 100. Right? So now I want to turn this transistor on, and if I want to turn this transistor on, of course the only way that I can do it is that I have V of S up here. It comes down here to this point, to the base of the transistor, goes to the emitter to the ground, and this current that goes through the base emitter junction has to be large enough so that it basically causes a large enough current in the collector emitter path of the transistor so that the transistor is turned on properly. So first I need to know how much current I need in the collector emitter junction of Q3. So in order to calculate that, so basically a transistor is said to be turned on if there is no voltage drop across the collector emitter junction, meaning that if I take this voltage over here and call it V of C, for example, this V of C has to be equal to 0. For this voltage to be equal to 0, the whole, basically you can see that this power supply comes all the way up to here, and then it goes through R5, and then the collector emitter junction of the transistor, and then it goes to ground. This is V of S positive. This is R5, and this is the collector emitter junction of the transistor, right? So this is a simple basically series circuit, and the voltage drop across basically each of these components, if you add those voltage drops, that has to add up to V of S, your supply voltage, right? So that means that if the voltage over here is supposed to be 0, the voltage over here over R5 has to be V of S itself, which means that I want the voltage drop essentially across R5 to be equal to V of S, right? And V of S in this circuit is 25 volts. That voltage has also been given to us. So that means that I can simply apply the Ohm's law to this resistor. And so one interesting thing about electricity and electronics is that basically you can see that this resistor over here, the value of this resistor is set. Of course you could choose another resistor, that's not a problem, but let's suppose that we cannot change this resistance, but by changing the current that goes through the resistor, I can change the voltage drop across the resistor. Normally you cannot do that, but the transistor basically enables you to do that exactly, which is something very interesting. I never actually thought about it this way. So normally what happens is that basically you have this resistor over here, it's connected to a power supply, for example. You have some V of S here, you have some R here, and then based on that you will have some current, and this current you have no you have no control over it. I mean, the only way that you could control this current would be changing the voltage here or changing the resistance here. Based on these two, this would change. Otherwise, you couldn't manually take your current and change it, crank it up or crank it down or something like that. Normally, you couldn't do that. But the transistor actually allows you to do that by basically by the way that it internally works. You have this NPN transistor, for example. You give this, you connect the emitter to the ground, the base. Basically, you put the resistor over here so that you can control the current here, and you connect it to V of S positive. This collector, you connect it to a resistor, and again connect this to the same power supply rail, the positive here, right? And so basically what happens is that this transistor is an NPN bipolar junction transistor. So the way that it works is that this is your I of B, and this is your I of C. And there is this relationship I of C to I of B is equal to beta. This beta is set for every transistor, at least for different currents and for different voltages. Your beta is a predetermined value for every transistor. And so this relationship actually exists between I of C and I of B, meaning that this ratio is always the same. Meaning that by changing I of B here, since beta is constant, then I of C can be changed, of course. Which means that, for example, basically the higher you choose based on the algebra that you see here, the higher that you choose the value of I of B, the higher the value of I of C is going to be automatically, because this beta is going to remain constant, right? So this basically means that if I play with this voltage over here, or with this resistance value over here, I can change I of B, right? By changing I of B based on this relationship, I can change I of C, which means that essentially I have control over this current that goes through this branch over here to the ground. And when I basically, let's call this R of C, for example, let's call this R of B, and since I have control over this current, if I basically apply Ohm's law to this resistor over here, V is equal to IR. So basically, let's say that this R is set. I cannot change that. Now I can basically, since I have control over this current over here, that means that I have control over this voltage over here, because these are on the two sides of this equation. And if I increase this I, which I can do using this transistor by making some arrangements in the base path, then basically what happens is that this voltage has to rise. If I decrease this current, this voltage has to decrease as well, which means that the voltage drop across this resistor can actually be controlled. That's what a transistor actually does. So that's something interesting that happens in transistors. Of course, you need to read the data sheets of these transistors and see basically there is usually different data. There is usually different beta values for transistors. For example, 2N2222A. If you look for this, you can see that let's say that, for example, let's take this document here, for example. I don't think this data sheet is going to be good enough, but you see over here, if I can make this a little bit larger, you see over here, it tells me that this is a TO92 package transistor 2N2222A, and these are the dimensions and everything, which is not important. This is the maximum ratings, collector emitter voltage, collector base voltage, emitter base voltage, collector current 600 milliamp continuous, which is way too high for such a small transistor. And this is the total device dissipation, 625 milliwatt, and this is the junction storage temperature, and so on and so forth. But then when you come over here, you see over here DC current gain. It tells you that the DC current gain is basically the same beta that we are talking about here. So for example, you see that for I of C is equal to 0.1 milliamp and V of C is equal to 10 volt, then the beta of transistor, then your beta becomes 35. And meaning that if you have 100 milliamp of collector current and the voltage across collector and emitter is 10 volts, then your beta is 35. And if you decrease this current to 1 milliamp, then basically, and keep the same voltage, then your beta goes to 50, and so on and so forth. So basically, you need to pick basically the voltage that's somewhere over here. The voltage has to also be equal to 0, which has not been given here. It's essentially supposed to be, I think basically this data sheet is not really giving us good information, but usually in other data sheets you see that, for example, somewhere it says V of C is equal to 0 volts or something like that, or something like 1 volt or something like that, and that means that at that beta, for example, the transistor can be turned on, right? Or goes into saturation, basically. Now anyway, basically any of these transistors that you want to use, of course you have to understand how that transistor behaves based on these graphs and everything. You have to take a look at these graphs and see if that's the right type of transistor for you. Usually they perform differently in different regions, so you have to pick the transistor that performs properly in the region where you need it. For different types of applications you use different types of transistors, of course. But essentially that's basically what the transistor does. I mean, it allows you to control the current here, which means that you can actually practically control the voltage drop across, for example, this resistor over here, which is something very very interesting and very useful in many types of applications. Anyway, so now I want to basically find the collector current that in such a way that basically the voltage drop across this resistor becomes the supply voltage, right? And that means that there is no voltage across the collector emitter junction. So how do I do that? So if I apply the Ohm's law to this to this resistor R5, I want the voltage across this resistor to be 25 volts. And I don't know what the current is for that sort of situation. And I know that basically this resistor is a 10 ohm resistor, which means that I is the same thing as 25 volts divided by 10 ohms, which is equal to 2.5 amps, right? Which is equal to 2.5 amps. That means that if I call this current over here I of 1, 2, 3, and 4, let's call it I of 4. Let's call this current I of 3, for example. Call this current I of 2, and let's call this current I of 1. Then I of 4 has to be 2.5 amps. I of 4 has to be 2.5 amps. If it's supposed to be 2.5 amps, that means that this 2.5 amps, you have to get this transistor to drive 2.5 amps into the collector emitter junction of itself, right? Which means that you have to use basically I of C to I of B is the same thing as beta for this transistor Q3. And basically I of C over here is this collector current, which is supposed to be 2.5 amps. So that means that 2.5 amps to I of B is supposed to be equal to the beta of this transistor, which is 20, right? Which is 20, which means that 20 times I of B is the same thing as 2.5 amps, which means that I of B is equal to 2.5 amps divided by 20. And if I divide by 5, I'll get 0.5. I'll get divide by 5, I'll get 4. 0.5 divided by 4, or let's say, I don't know, 2.5 divided by 20 is the same thing as 0.125. 0.125 amps, right? Amps. That is basically the I of B over here. That is I of B, which is basically this current I of 3. That means that I of 3 is supposed to be 0.125 amps. So now if I want to have this current in over here as going through R4, I have to choose the right value of R4 so that 125 milliamps of current is flowing through this branch, because this branch, basically the current going through this branch is actually regulated by this is determined by this resistor, right? So then I can basically choose the right resistor over here, right? So I apply the Ohm's law to this resistor R4, which means that V is equal to IR applied to R4. Now this R4, as you can see, there is the supply voltage up here, goes through this resistor, goes through this PN junction, and then goes to the ground, right? Now the ground over here, the PN junction, the voltage drop over here is 0.7 volts, which is negligible. You can ignore it. There is no problem with that, because your supply voltage is 25 volts. As long as your supply voltage is over 10 volts, you can ignore all of these voltage drops across these PN junctions. There is no problem with that. which means that, so the supply voltage comes from here through the resistor, through the PN junction to the ground, which means that I can assume that the whole supply voltage is across this resistor, really. I mean, I can ignore the PN junction, which means that basically 25 volts is across the resistor R4, and the current going through this resistor is supposed to be 0.125 amps and times R, basically. That means that R is equal to 25 volts to 0.125 amps, which is the same thing as basically, what is that, 25 times 5 is 125. So if I divide by 5 here, I get a 5. If I divide by 5 here, I get a 25, and then if I divide by 5, I get a 1. If I divide by 5, I get a 5, 0.005. So that's 1 by 5,000, which is 1,000 divided by 5, I suppose, right? So 1 divided by 5,000 is the same thing as 1,000 divided by 5, which is equal to 200. So that's supposed to be 200 ohm. So let me see if that was correct. 25 by 0.125 is 200, right? Okay, so that means that this resistor R4 over here is supposed to be 200 ohm. This resistor R4 is supposed to be equal to 200 ohm. When you have this resistor over here, the current I3 becomes 125 milliamp, and then this current over here becomes 2.5 amp, and that means that this transistor is turned on, right? So that's how you turn this transistor on. Now you need to use the same strategy in order to turn all of these transistors on, and that's really basically all the same thing, meaning that you have to see how much collector current you have, how much base current you need, and based on that put the resistor over here. Again, the same thing for Q1 and so on and so forth. Okay, so now we have decided that basically R4 is supposed to be 200 ohm, which means that and we cannot, of course, we cannot change it, otherwise that the rest of the circuit is going to be disturbed. So now we are moving in this direction towards the left, basically, right? So we cannot change this anymore. That means that this I3 that is 125 milliamp, that is the collector current of Q2, right? So now I can write basically I of C to I of B is the same thing as beta for this transistor Q2. And I know that and I want to turn this on, basically, right? So that means that the collector current of this transistor is basically this I3 that if the transistor is turned on, the current goes from the supply voltage over here through to this resistor, through this resistor, and through the PN junction, and then back to ground, basically, right? So then 125 milliamps, so 125 milliamps or 0.125 amps to I of B is supposed to be basically the beta of this transistor Q2, which is 50. So So now solving for I of B, we have 50 times I of B is the same thing as 0.125 amp, which means that I of B is the same thing as 0.125 amp. Is the same thing as 0.125 amp divided by 50. And if you do the calculation, divide by 5, you will get 125 times 25 is 5. So that's a 25 here, 0.025, and divide by 5 you'll get 10, and again divide by 5 you'll get 5, so that's 0.005, and you get 2 over here. That's 5,000 divided by 2, which is the same thing as 5,000 divided by 2 is the same thing as 5,000 times 1/2, which is the same thing as 5/2000. 5/2000 is the same thing as divided by 5. So essentially 20 divided by 5 will get a 4. That's it. Divide by 5, 1 divided by 20 divided by 5 is 4, and then you get the 400 there. 1/4 is the same thing as 0.25. 0.25 divided by 100, you will get 0.0025, right? I suppose, right? So that's the same thing as 0.0025 amps. I'm not really sure if that was all okay. And divide by 50 is 0.0025 amps, right? So so that means that the current this base current of this transistor is supposed to be basically, or I of 2 is supposed to be 0.0025 amp. And as you can see, as we are moving towards the left hand side of this circuit, these currents are getting smaller and smaller, meaning that over here the current was 2.5 amps. Of course, that depends on that. I mean, the rate at which these currents are getting smaller does depend on the beta of these transistors. The larger the betas, the faster you will get to smaller and smaller currents, because every time that you move to the base of the same transistor, basically the base current is going to be 1 divided by basically 1 divided by beta of that transistor, meaning that the collector current is actually always beta times the base current of the transistor. I don't want to confuse you, of course, but essentially this is the relationship, meaning that, as you can see here, the collector current is always equal to beta times the base current, meaning that whatever the base current multiplied by beta, you get the collector current. So the collector current is always larger, of course, by a factor of beta, of course, right? So so that's basically that. So you know that basically I of 2 is supposed to be 0.0025 amps, and now we need the right resistor for that sort of current. So I of 2 is going through this resistor R3. If I write V is equal to IR applied to R3, I get again the same story. Basically, the voltage 25 volts of supply comes over here to through R3, through the PN junction to the ground, ignoring the voltage drop here. The whole voltage is dropped across R3, so I can write basically 25 volts is the same thing as the current through this resistor, which is 0.0025 amps, times the resistor value, which means that R is equal to basically 25 volts divided by 0.0025 amps, and that's the same thing as divided by 25. 1 divided by 25 would be 0.0001 amp, which gives us 1 divided by 1/10,000 is the same thing as 10,000, right? That's 10,000 ohm. So that means that R3 is supposed to be 10,000 ohm, which is 10 kilo. Right? So now basically we know that basically R3 is 10 kilo ohm, and the current going through this I2 is this current 0.0025 amp, and that becomes the collector current of Q1. Again, I can say I of C to I of B. Now I want to turn Q1 on, right? Now I want to turn Q1 on. So to turn that on, I need to know how much collector current I need, or essentially I know that the collector current is basically this collector current, right? And now let's see what happens here. Let me think in a different direction. So now if I have this I2 over here, which is 0.0025 amp, and if I have this resistor over here, which is 10 kilo ohm, that's going to be 25 volts, right? Right. So you see that this transistor with this current, with this collector current and this resistance value, is already saturated. Of course, provided that enough base current flows through the emitter, through the ground. Meaning that over here I have a current of 0.0025 amps, right? So I of 2 is equal to 0.0025 amp. And R3 is basically 10 kilo. Now the voltage drop across, if this current basically goes through this resistor here, you know that V is equal to IR, so that means that the voltage drop across this resistor would be I, which is 0.0025 amp, times basically R, which is 10 kilo ohm, which is basically 10,000 ohm, and 10,000 times 0.0025 is the same thing as 25 volts, which is equal to the supply voltage, which means that the whole supply voltage is across this resistor. There is no voltage across the collector emitter junction, and then that means that Q1 is turned on, is saturated. So basically we have no problem. What I meant to say is that we have no problem there. Now, what is important here is that this current of basically whatever that is, I don't really, I mean, whenever I don't have to, I really don't convert these currents. But this is weird. I mean, I don't know how much current that really is. You're usually familiar with milliamps, microamps, and that sort of thing, but this, for example, would be 2.5 milliamps, right? This would be 2.5 milliamps. Okay. Now, so over here, basically, I want I want 2.5 milliamps to be flowing here, I2. That means that again I can write I of C to I of B is the same thing as beta and apply it to this transistor Q1. Now in transistor Q1, I of C is basically this I of 2, which goes in this branch, which goes into this branch. That means that 0.0025 amps divided by I of B is the same thing as your beta of Q1, which is 100. Now divide both sides of this equation by 100, you will get basically let's multiply 100 times I of B is equal to 0.0025 amp, which means that I of B is the same thing as 0.0025 amp divided by 100, which is equal to basically 0.000025 amp. So that means that basically I1, this current, this base current is supposed to be this current over here. I1 is supposed to be 0.000025 amp. Of course, these numbers you have to write in scientific notation, but I mean, as long as I can get away without conversion, I don't really do it, because it's really not necessary right now to do that. So basically this current is supposed to be this current over here. So I can essentially say that it's basically 25 microamp, right? It's 25 microamp. And so if I to choose this resistor, I apply Ohm's law to R1, and again the whole supply voltage is across R1, so that's 25 volts is equal to this current. That's 25 into 10 raised to the power negative 6 amp. 30 and 6, negative 6 amp times basically R, which is this R1 over here, which means that R1 is the same thing as basically 25 volts divided by 25 into 10 raised to the power negative 6 amp, which is the same thing as, simplify these, you'll get 10 raised to the power 6 ohm, which is basically 1 mega ohm. So that means that R1 is supposed to be 1 mega ohm, and then basically what happens is that for this resistor here, which ties the base of this transistor Q1 to ground, you can just simply arbitrarily choose the same value, for example, over here, or any other value really of any other resistor here. For example, you can choose it to be, well, not 200 ohm, but for example 10 kilo ohm, or you can choose, well, you can go all the way up to 1 mega ohm. Usually basically what they do, they arbitrarily choose some value which is the same value that is present in the circuit, because the fewer number of part numbers or component numbers, the components that or different values of components that you have in a circuit, easier it is to put together a circuit. Basically, when there is variety, then the circuit gets more and more complicated. And any value for this resistor that you choose between, for example, say 10-20 kilo ohm all the way up to 1 mega ohm, it's going to do the job. It's just to make sure that this transistor turns off, meaning that no current could ever flow to the base of this transistor when the switch is set to position B, right? and I don't really know why they do that. It's just like the what do you call it? The tricks of the trade or something like that. This is based on testing and experience and that sort of thing. Engineers usually do this type of thing, meaning that when they want to tie something to some node in the circuit to the ground, and to make sure that no current can ever flow to that node from the supply voltage, they put a resistor over there for whatever reason I don't really understand. Anyway, so these are the resistor values. Now let me check our answers here and see if the answers are correct. And then, so R4 is 200 ohm, correct. R3 is 10 kilo ohm, correct. R2 is 1 mega ohm, correct. And R1 is 1 mega ohm. So all of these values are correct, and you can use these values in your circuit. Okay, so I think we have done enough of these examples. I think I'm going to do one more example here related to a circuit again, the same type of example, a little bit different, about basically turning on and off a transistor, an NPN transistor. So I'll see you in the next video, and thank you.